welcome back. We are looking at the rate monotonic scheduler and we had looked at some issues, the schedulability analysis and also looked at the transient overload handling and so on. Now, let us look at some specific points that we need to understand regarding the rate monotonic scheduler. One is that how does the rate monotonic scheduler work with harmonically related tasks. We say that a task set is harmonically related if given that any task has higher period than another task, then it must be a multiple of the lower period task. Or in other words, if we take any two tasks in the task set T I and T k, let us say, and we find that the period of T I, which is P I, is greater than P k, then P I is some multiple of P k, and that holds for every task in the task set. Whenever we take two tasks, if one task has higher period than the other task, then it must be a multiple of the other period. Just to give an example of a harmonically related task set, let us say for the T 1, the task 1, the period is 10, for task 2, the period is 20, and for task 3, the period is 60. In this case, you can check that if we take two arbitrary tasks T 1 and T 2, okay, T 2 is greater than P 2 is greater than P 1, but then it is a multiple of P 1. If we take P 2 and P 3, P 3 is greater than P 2, but again P 3 is a multiple of P 2. So, that holds for every pair of tasks. So, this is an example of a harmonically related set of tasks, and this is of special interest to us because something very unique happens here. If a task set is harmonically related, then the schedulability criterion becomes that the utilization, even if the utilization is 1, still the task set becomes schedulable. Let us say we have 10 tasks with task periods that are harmonically related, and if you use the Liu Leyland criterion, you will get something like 0.7. Less than 0.7 utilization, task set will not be schedulable. That will be the application of the Liu Leyland to any task. But then here in the harmonically related task set, even if the utilization is up to 1, still the task set remains schedulable. But how do we show this? Now, let us through a simple mathematics, let us show that any harmonically related task set is schedulable under the rate monotonic scheduler as long as its utilization is less than or equal to 1. How do we show it? Let us try the completion time theorem. We know that the completion time theorem for every task set, we must have E I and the time taken for the task T I, we need to check whether its execution time plus the time taken for executing all its higher priority tasks that arrive before its period is less than equal to its period. But for a harmonically related task set, we know that P I and P k are multiples of each other. So, P I is a multiple of P k, and therefore, we can get rid of the ceiling because it perfectly divides, P I perfectly divides is divisible by P k. Therefore, we can take out the ceiling and we can write E k by P k. So, E I by P I, so we have divided P I all through. So, we write E I by P I and sigma k equal to 1 to I minus 1 E k by P k, the P I had come out from the ceiling and therefore, P I is cancelled by the division, and therefore, we write E I by P I sigma k equal to 1 to I minus 1, E k by P k is less than 1, or we can rewrite this expression as I equal to 1 to n E I by P I is less than 1, less than equal to 1. So, by the completion time theorem, we can show that as long as the sum of the utilization of the task set is less than 1, then it will meet its deadline. If we compare our whatever we learnt about the rate monotonic scheduler and the EDF, we can see that the rate monotonic scheduler has a lot of advantage. Its implementation is more efficient in a multi-level priority queue. Of course, the processor utilization is slightly lower than the EDF, and we will look at the context switches, slightly more context switches than the EDF, and the guarantee test is slightly non-trivial. We need to check the Liu-Lehoczky or the Liu-Leland criterion, whereas the EDF is simple, the utilization, sum of utilization is less than 1. The rate monotonic scheduler is overwhelmingly popular, used in many applications, space applications, advanced automation systems, large number of embedded applications, even has influenced the specification of the IEEE future bus, and in many time critical applications the rate monotonic scheduler is used and is supported in almost every real time operating system. Now, let us look at certain rate monotonic scheduler generalizations, because it does not handle certain conditions, the simple algorithm that we looked at. We need to have certain other enhancements that will cater to these situations. The first one we look at is the deadline monotonic algorithm, just a small variation of the rate monotonic algorithm, and this we need to use when the task deadline and periods are different. If you would have noticed, in all our examples so far, we considered the task period and deadline to be the same, but there can be situations in practical applications where the task deadline and period are different. For example, deadline may be less than the period or deadline may be more than the period. Of course, deadline being more than a period is extremely rare, whereas there are many cases where the deadline is less than the period. So, in cases where deadline is not equal to the period, rate monotonic algorithm is not really the optimal scheduling strategy. For these cases, the deadline monotonic algorithm is the optimal. But what is the main idea behind the deadline monotonic algorithm? It is very similar to the rate monotonic algorithm, excepting that the priorities to tasks are assigned based on their deadlines rather than their periods. So, even if a task has higher period than another task, but it has a lower deadline, then that gets higher priority. First, let us answer this question that do RMA and the DMA, rate monotonic algorithm and the deadline monotonic algorithm, both of them, do they produce identical schedule under some situations? With little thinking, we can say that if the period and deadline are the same, then of course, the deadline monotonic algorithm it simplifies into the rate monotonic algorithm. But for arbitrarily relative deadlines, where the deadline may be different from the period, they may produce different schedules. For example, Even when the rate monotonic scheduler fails, the deadline monotonic scheduler may come up with a feasible solution. But on the other hand, whenever the deadline monotonic scheduler fails, the rate monotonic scheduler will definitely fail. We will not really look into the mathematical theorem proof behind this statement, we will just assume at its face value, but then in the books that we refer, proofs are available, you can go through, but for our purpose we will just use it at its face value, that the deadline monotonic algorithm can produce a feasible schedule when the rate monotonic scheduler may not. Whereas, whenever the deadline monotonic scheduler fails, the rate monotonic scheduler will also fail. Now, let us look at one example. We have a task set consisting of 3 tasks T 1, T 2, T 3. Their execution time, period and deadline is given. Now, we need to check for their schedulability using the rate monotonic algorithm and the deadline monotonic algorithm. If you apply the rate monotonic algorithm, the task T 1 is the highest priority task, task T 2 is the second highest priority and T 3 is the lowest priority task. But in the deadline monotonic algorithm, task T 2 is the highest priority task because it has the lowest deadline, task T 1 is the second highest priority task and task T 3 is the lowest priority. This indicates that the priorities assigned to the tasks are different, and the difficulty here is that the results that we got for the rate monotonic analysis, that is completion time theorem, Liu Leyland criterion, etc., would not apply to the deadline monotonic algorithm, because here the deadline assignment is different than the rate monotonic algorithm. But then we can check it manually. So, you can check the Liu Leyland criterion for the rate monotonic analysis, we find that it is unschedulable, and we can do a completion time check for the deadline monotonic algorithm and check whether all the task set meets their first deadline, and we see that the task set is schedulable under the deadline monotonic algorithm. Now, let us look at another aspect which is also practically important, is the context switching. The context switching time for operating systems is substantial sometimes compared to the small task execution times. The task execution times are of the order of few milliseconds, maybe 50 millisecond or 20 millisecond, maybe 10 millisecond, whereas the context switching time is typically 1 millisecond or so. So, when we have task deadlines and the task execution time so close, so comparable to the task to the context switch times of the operating system, we cannot really ignore them in our analysis. But then if we really want to include that in our analysis, how do we do it? Let us look at that point. The crux of our solution here about how to handle context switching in the rate monotonic analysis is to consider the following situation, that when do the task preemptions occur, and whenever task preemption occurs, we need to consider the context switch time. One task preemption can occur when there is a lower priority task running and then there is a higher priority task which has arrived, then the higher priority task preempts the lower priority task. And also when the highest priority task completes, again the lowest priority task resumes its execution. So, there is again a context switch. So, in the worst case we can assume that each time there is a task that arrives, it may at most cause one context switch, because the task that may be running is context switched, and again when it is on its completion there may be a context switch. But then as you can easily look through this, that this is a very conservative analysis, because we are assuming that each time a higher priority task is running, a lower priority task is running and a higher priority task arrives and there is a context switch. But we are overlooking that sometimes a higher priority task may be running and a lower priority task arrives and there is no context switch. But then in the real time systems, all our analysis are conservative analysis. We look at the worst case and do a worst case analysis. So, from that point this is quite okay, that we assume that whenever a task arrives it causes two context switches. One, the running task is context switched and the arriving task is taken up for running, and the second, on completion of the task, the one that was already context switched resumes its run. So, there are two context switches for every task arrival. And once we understand that, then the answer about how to take context switch overheads becomes extremely simple. So, we assume that each task instance, that is each job, incurs at most two context switches. When it starts to run, preempts the currently executing tasks, and when it completes. Now, let us assume that the context switch time is constant c, that is the worst case context switch time is let us say c millisecond. So, we can take the effect of context switching by just adding 2 c to the execution time of every instance of the tasks. So, in effect we just transform our task set into one where execution time of every task is increased by 2 c. But then of course, you may agree or you may argue that see the lowest priority tasks, the never context switches any task. Why do we consider 2 c for that? It can be 1 c, like nothing was running and it started to run, maybe 1 c, but then we are doing a worst case analysis and for every task we increase it by 2 c. So, this is an example. We have a task set of 3 tasks T 1, T 2, T 3 and their execution times are 10, 25 and 50 millisecond, periods are 50, 150 and 200. And we assume that the context switch time is 1 millisecond and we want to check whether the task set is schedulable. To take the context switching time into account, we need to increase the execution time of every task by 2 millisecond. So, our new task set becomes 12, 27 and 50 millisecond. So, that was 10, 25 and 50. So, it will become 12, 27 and 52. So, we check whether 12 millisecond is less than 50 millisecond. So, that is task T 1 has the highest priority, find that it is schedulable. Similarly, we check for the second task 27 after taking 2 context switch into every execution instance. The higher priority task can arrive at most 3 times. So, this is also schedulable. For task T 3, we need to check that 52 millisecond after taking the context switching into account, and it is 2 higher priority tasks that take, this is the execution time in each period, and therefore, it is also schedulable. So, considering the context switch time under the simplified assumptions that we consider the worst case context switch time, and also we assume that every task arrival causes 2 context switches. So, under that we can do an analysis for a practical situation. There are some practice problems, please do it. One is check whether the following task set is schedulable. We have T 1, T 2, T 3, 3 different tasks with different execution times and periods, and we assume that the context switch overhead in the worst case is 1 millisecond. The effect will be to increase the execution time by 2 millisecond. So, this will become 11, 7 and 12, but what about the priorities of the tasks? Which task will have the highest priority? So, we look through the period and find that T 2 has the lowest period, and that has the highest priority, priority 1 for T 2, priority 2 for T 3 and the lowest priority for T 1. Now, let us examine another situation, that what happens if some task is extremely critical, but then it is not the shortest task, its period is larger than some tasks, but this task is more critical than the other tasks. How do we handle this situation? Because in a simple rate monotonic priority assignment, we just assign priorities based on the frequency of occurrence or the period of repetition, and then in that case the shortest period will get the highest priority, but we know that some task with higher period has most criticality. How do we handle this situation? Because simply giving it a highest priority, that will make our all the schedulability results unusable. If a task period is 100 and we assign it priority 1 when there are other tasks like 20, 50 etc., and they are given lower priority, then all our Liu Leland, Liu Lehoczky's criterion etc. will be difficult to use. So, a solution proposed by Shah and Rajkumar, known as the period transformation method, 1989. So, this is a standard technique to handle situations where a critical task has a long period or its frequency of occurrence is lower. The main idea here is that we divide the critical task into smaller subtasks. We do not really physically subdivide, we do not really take out the code and start dividing, it is only for analysis. So, what we do is we just consider its execution time and we want to split it into k parts. We assume that each part runs for E I by k and deadline d I by k. So, if you want to split into 2 parts, so and the task execution time was let us say 50 and period was 100, we assume that it is actually 2 tasks, each one execution time 25 and period is 50. So, that way we have increased its priority and still the Liu Leland and Liu Lehoczky's results become applicable. So, the task splitting is done at a conceptual level rather than making change to the code itself. let us take some example. Let us assume that we have two tasks. T 1 requires 5 millisecond every 20 millisecond and T 2 requires 8 millisecond every 30 millisecond, and T 2 let us assume that it is the critical task. So, it should not miss its deadline on account of T 1. We need to give a higher priority to T 2. In that case, what we do is we consider that T 2 consists of two tasks, T 2 A and T 2 B, each one having execution time 4 and period of 50. And then we can use the rate monotonic analysis results. The next question comes is that how do we handle aperiodic and sporadic tasks? If you remember that aperiodic tasks are tasks that arrive randomly, but then they do not have a deadline, whereas the sporadic tasks which arrive randomly, but they have some deadline before which they must be completed. If we give priorities to sporadic tasks, then it would make our real time scheduler unusable, because many of the slots will go empty, because the sporadic task arrives randomly, and it may lead to a situation where the system is cannot schedule the regular periodic tasks, and also the sporadic tasks may occur randomly in close succession, and therefore, it will make the lower priority tasks miss their deadline. So, the solution to this is a aperiodic server technique. Now, we are almost at the end of the lecture hour. So, we will just look at the aperiodic server, that is how to handle the sporadic and aperiodic tasks within the rate monotonic framework in the next lecture. Thank you very much.